Yeah. Let us start our BIM's Integrable System seminar today. Our speaker is Hutsalyuk from CISA, and about exact correlators in integrable circuits from algebraic geometry.
Okay, thank you for invitation. Let us start. I will talk indeed today about this paper that about this project that was done with collaboration with few my co-authors, in particular Yunfen Jiang, who you all know. He together with me was doing mostly analytical part of this project. Balazs Poshgai, who was inspirator of the project and connected this all to integrable quantum circuit, and then there were two guys, Herfenich and Young, who performed mostly very important and in some way key part of the work, that is computational part. And indeed, I would be talking today about some specific computational technique that is called algebraic geometry. In fact, there will be not too much algebraic geometry. It raises a series of polynomial rings, but you will see details. Okay, let us just start from some simple setup, and let's just start from what exactly we consider, and I will also give motivation why this particular setup was considered. So the basic idea that we want to study the evolution of one-dimensional spin chain with some initial state, and then its state is evolved in time, in discrete time, using some Fouquet evolution, or if you wish, it's called totalization procedure. So we have one-dimensional system with sides 1, 2, 3, 4, and up to 2L. The lengths in our case will be always 2L. And then this is spatial direction, horizontal direction. Could you see my mouse? Yes. Sorry, could you see my mouse? Yes.
Hopefully. Yes, we can see.
Yeah, beautiful. And vertical direction is a discrete time direction, so Trotter direction. So in this vertical direction, it's time propagation. And the time propagation is given by consecutive action of this row operator that in fact is nothing but transfer matrices. And as you see, it's organized in a very specific way. So at the step number 1, we act with this two side operators that acting on side 1, 2, the next operator side 3, 4, and so on. And then on the next step, this structure is shifted by one side. And this is important, otherwise, of course, evolution would be just trivial. And as you see, this evolution operator is periodical with size 2. So in fact, our evolution operator, or our transfer matrix, would be also called a double row transfer matrix, is this two line. And we call these lines even and odd, U, O, U, E. Well, this is just analytic representation of them, explicitly written via this unitary arc check. And as I see here, I identify this unitary gate, or this evolution operator just for two sides with some arc check. And this is not coincidence. You will see that indeed I choose U to be some 6-vertex matrix. And I already said the word unitary. This is standard terminology, and indeed, even if we, in general case, this U should be choose to be unitary operator in order to have time reversal symmetry. Otherwise, it would be sort of unphysical. So what else we need here? But well, basically we introduce time evolution in this time direction. Okay. And what this particular setup is interesting for us, in particular, our main idea of this project started from the paper of Igor Alainer, who works in Google Quantum, and this paper is published in 2021. It's Bethe Ansatz solutions for certain periodic quantum circuits. So what was the main motivation behind this work for Igor Alainer himself? Of course, it's Google Quantum. Because if you see let's back for a second to a previous slide. If you see here, basically what we have from the point of view of hardware, if you wish. We have some initial state and we have some two-side operators that act consequently on this initial state and produce at the very end something. And this is the very basic and very convenient setup to run on the quantum computer. So usually when you perform some computation in quantum computer, you need to map your program somehow on the basis of qubits. Exactly in the same way as classical program should be somehow mapped on usual basis of 1-0. And quantum spin chain is the most convenient setup because basically you are mapping problem onto itself. You already have spin 1/2 problem and you perform mapping it onto spin 1/2 problem. So indeed, this quantum circuits, it's very typical setup to test and perform tests with quantum computers. But of course, if you perform tests, you want to know what you get analytically. And Igor Leiner indeed made this attempt to compute something, but his paper was not finished. And in fact, our paper is sort of we finished his job in our computation. And he considered in his work he made few choices for unitary gates. One of choice was nothing but Hubbard model, and another choice was this unitary gate, this two-side operator. It acts in tensor product of two local spin 1/2. And as you can easily see, with some certain reparameterization, it would be nothing but 6-vertex armatics or rather arc-check with some diagonal twist. That, of course, diagonal twist doesn't create any problem for integrability. It's perfectly known. And this would be the main setup with which we will work further. So, okay, just a few basic notations about typical integrability. So this is 6-vertex armatics or arc-check. It's parameterized by two functions C and B that itself are expressed either via sinh, either via linear function. So it depends whether we consider here anisotropic case as an isotropic case. Technically, I wrote here sinh and cosine hyperbolic, but in reality, it doesn't matter for us whether we in massive phase, whether we are in massless phase. Both cases could be considered in our approach. And within this, within this proper choice of function B and C, we know that our system is integrable. So this armatics satisfies certain equation called a Yang-Baxter equation, and we define in absolutely usual way monodromy matrix could be defined that is given by elements A, B, C, D, and transfer matrix could be defined as a trace of monodromy matrix, and then it's there would be transfer matrix become a generation function of conserved set of charges. Actually, it's not too important for us. I just want to stress that we have very typical integrability setup, usual 6-vertex model, and there would be just, because we are working with integrable circuits, there will be just very minor differences with respect to usual case that I would specify in next 2 slides. Let's just now clarify that, okay, we have usual vacuum state. So vacuum state I denote as tensor product of 2 L local spaces. So 0 means just spin down. And then we know how to build eigenvector of the system with k number of magnons. It could be as many as 2L magnons, as low as 1 magnon, or it could be even 0 magnons. And beta vector is built in absolutely usual way, just a product of B operator from the monodromy matrix. Then we have eigenvalue problem that is defined again in the absolutely usual way. That these functions, these vectors, call it beta vector, would be eigenvector of the transfer matrix if this set of spectral parameter un or uk satisfies certain type of equations, call it Bethe equation. So I don't think there are any problem here. Just modulo 1 clarification. We use here in general inhomogeneous system with some inhomogeneities, and the system size is again 2A, not singular. And now I want to specify what is specific related to the quantum circuit. In fact, it's not too much. So since we are dealing with this double row transfer matrix, you remember this gates even odd this two row monodromy matrix that become two row transfer matrix. As I define in integrable circuits, what is required here for us? It's required to specify a set of inhomogeneities. And specification is following, that at even sides, this set of inhomogeneities is chosen to be u over 2. On the odd sides, it's chosen to be minus u over 2. That's all. And correspondingly, Bethe equations here are modified in the following way. Well, just written explicitly what was in the previous page. I don't know, hopefully it doesn't need too much clarification. And quantum inverse problem, well, it exists, but probably I even skip these details because it's not too important for us how exactly quantum inverse problem organized. In fact, yeah, it's not even needed. Let's in the very end, we are using previous results in this part, so probably details of Bethe Ansatz are not even too important. What is important for us? What I want to specify explicitly, what our initial states, because this is like key moment in our initial states is this specific domain rules. So what we have here, we have that we have in total 2L system size, and first n qubit or first n sides spin are flipping up, and the rest spin is down. And the flip is performed basically by action of this operator onto vacuum state. If you remember, omega is just vacuum, so omega is a state where everywhere is zero, and this operator acting on the first n side just flip spins. And this operator sigma hat, what does it mean? That k it's more, so this is just string of sigma x operators, and it starts from side k plus 1, and it has length n. So all on n consecutive sides are involved. And in what we want to calculate, in fact, is dynamic correlation function. So we start from this state, from the left domain wall, and move to right domain wall. And in fact, it's equivalent. We consider correlation function between two vacuums of these strings. So here is operator is taken at side k. The second operator is taken at side 0. Both operators have side length n, and one is operator is taken at time 0. The second operator is taken at time n. And what mean time n? Time for us, it's, as you remember, it's vertical direction. Its propagation in time is given by this double row transfer matrix. And if in fact we just this means that we switch it to Heisenberg picture. So at the very end, we want to compute this expectation value, and how we would deal with it. Okay, we deal with it with usual manner. It's not even our trick. It was known for a long time ago, and up to this formula, it was even in paper of Igor Liner. So formula is actually absolutely obvious. We insert between these two operators the full set of states. Resolution of identity as the sum over full set of states. The states un, so the states with n magnons. And okay, then what we get at the very end, we get this factor sum. What is here? What components are present? So this in denominator is just a normalization of eigenstates. So we know that this is Godin determined. This overlap between boundary domain wall or initial state domain wall, if you wish, and eigenvector of the system. And this we would discuss on the next page, how to compute it. Actually, it's very easy. And there are here two eigenvalues of two different transfer matrices. And it's easy to understand why they're present. So here, as you see, there is n. N, it's time propagation. So these operators here taking a different moment of time, and n is operator of the time propagation. So tau is eigenvalue of this operator. Obviously, it appears here since we have a dynamical correlation function. In denominator, we have this mu. Mu is eigenvalue of, should be here, not tau, mu. Mu is just eigenvalue of operator of space translation. Because indeed, these strings of the same length, but they are shifted in space as well, or there is spatial separation between two operators. Again, naturally, that these eigenvalues appear in this four-factor series. I think four-factor series is pretty standard. Any question up to this moment? Okay, so let's move fast. And okay, at this moment, as I mentioned, we need overlap between two. We need this overlaps. We need overlap between eigenstate of our transfer matrix, and we need overlap between boundary or initial state, if you wish. And this overlap, in fact, can be very easily obtained from usual Slavnov determinant. What is Slavnov determinant? It's some form of determinant representation for the scalar product between on-shell or on-shell beta vector or eigenvector of transfer matrix and generic beta vector. And the determinant representation was found by Slavnov in 1989 for such type of overlaps. And taking the proper limit in this determinant, we can obtain some certain representation, also determinant representation for this type of overlap. I don't give details here because they are not important, and they are known for years from the paper of Cohen-Mosel, I believe, 2007. Very simple and standard computation. Okay, at the very end, we obtain some determinant representation expressed via this function phi. As I can remember that phi is given by sinh in massive case, by sin in master's case, and by linear function in case of isotropic spin chain. Okay, G is expressed just in this way. And for simplification, to be fair, what I wrote here is the case of even numbers of Magnon. For odd number of Magnons, there would be some small modification, but probably details doesn't matter too much here. What is important, yes, you know, good representation for this type of overlap. Okay, and up to now, I was talking about integrability. I presented you four-factor sum. But okay, in four-factor sum, there is indeed a sum, and the sum taken over all possible solutions over Bethe equations. However, Bethe equations themselves is not a very convenient instrument to solve, because Bethe equation, they have few problems. First of all, there are some open problem with overcounting of beta roots, and there is very unpleasant problem with the presence of unphysical solutions. So when you obtain some formal solution of Bethe equations, you need to have some good idea of which solutions are physical, which are not. And in some moment, Bethe equations were formulated by Baxter via InTQ system. And further in 2017, in the paper Wallin and Barbeau, so-called fast analytic solver of Bethe equations, the following system, called QQ system, was proposed. What is written in fact here? Let us consider the system with M magnons, and in this case would be, we can identify the space of solution of our system with a certain Young tableau. In fact, again, I am afraid it's written here with error. So the setup is the following. We have the system of length L, let's say. then there will be L cells in this Young tableau, and the first row would contain L minus M, or vice versa. You can write the first row would be M. The M is number of magnons. It's error here. Should be M. And the second line would be L minus M. And then how you specify this Q? You specify A and S here as coordinates on this lattice. And functions Q are living in the nodes. So there is, at every node, there is some Q function. And there would be, in general, well, some amount of this functions Q. Q plus Q minus is just a shift of argument of this Q functions by this deformation parameter Q that is related to anisotropy of our model. In rational cases, would be just a linear shift plus minus 1. And well, A plus 1, AS here is just a subscript that characterizes particular Q function. And basically, this is some functional equations for our Q, and solution of Q, solving of this equation is equivalent to solving the system of Bethe equations. The only moment that should be specified here, it's initial condition, because or boundary condition, if you wish. Because when we have Young tableau, in fact, we should specify how Q looks here on this edge and on this edge. In the moment Q is specified, in some certain conditions were provided by Wallin and Marbeau in their paper, how to fix these functions. The solution of these functions indeed would be equivalent to solving a system of eigen values, so Bethe equations, if you wish. And okay, okay, so what is this Q polynomial? Q polynomial could be presented as this type of polynomial. So x is just a variable of polynomial, and xj are root of these polynomials. Equivalently, certainly it could be written in this way. And of course, coefficient ck should be fixed. It's just some coefficients. And there would be certain conditions that we call zero reminder conditions. Why it's called zero reminder, it would be clear a little bit later. Condition of this ck is following. We require that all Q functions would be polynomial. Because generally speaking, it's not obvious in general cases. Indeed, all Q could be written in this way. Why? It's not obvious. Okay, we assume that we substitute arbitrary polynomials here, 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 here. We have technically bilinear equations, and we have everywhere some polynomial, and what idea can come to our mind? Let us divide all right-hand side and left-hand side by these functions. So, okay, here are some combinations of polynomial, but we divide polynomial on the bipolynomial. And technically, it's not. We have some rational functions in the right-hand side. There is no guarantee that at the very end we get what we get would be indeed the denominator would somehow cancel out, and we get just polynomial. And the conditions that we get polynomial, it's so-called zero reminder conditions. Okay, so here I probably even finished with the integrability part per se. I defined all integrable objects, and now it's time to switch to a little bit technical part of the work, explicitly how to perform computations of this, how to deal with everything that we introduced earlier. Any question to this moment?
Look at this QQ system. So it's not easy to solve recursively starting from the left boundary. I'm just checking the details of the formula. The previous slide. You have formula. So if you know the values of Q's on the left boundary, right? That's what you're.
Yes. Well,
it's not easy to solve, right? Because right.
Yes,
so it's a complicated system.
Yes, I would say yes.
It's not like doing mutations when you just know what to do in which order. Okay, yeah, I was just checking. Yeah, thank you.
Well, technically, we know what to do, and zero remainder conditions, it's a requirement that this is polynomial, it's indeed would be some restriction of CK. However, okay, I would specify what is going on. In some sense, we're not even solving these equations explicitly here. You will see how it's proceeding a little bit faster. So, okay, probably I just switch to polynomial rings and explain general theory that was applied here. So let's introduce few mathematical objects. First of all, I want to introduce polynomial ring. It's the set of all functions that are polynomial functions of n variable x1, xn. Definitely this set of polynomials satisfy rings conditions. You can add polynomial, you can multiply polynomial, you still get polynomial at the very end. Then, on this ring, we can introduce ideal. And ideal, by definition, is a subset such that for every function f belonging to the ideals, if we have two functions, both of them belong to ideal, their sum belong to ideal. And then, if we have functions that belong to ideal and some function j, arbitrary function that belongs to polynomial ring, multiplication of function f by function j should belongs to ideal again. Very simple conditions. If we find we can find some ideal if it exists in our system, and then what we know that polynomial ring is Noetherian ring. So any ideal I of this polynomial ring is finitely generated. And what it means that there is some finite number of polynomials f in this ideal such that for any functions f belonging to the ideal, the following expansion could be made, whereas function f belonging to ideal and function j are just coefficients here that are in self polynomials, but not from ideal, just general polynomials that in general belong to the ring. And this set of polynomials, f1, fk, they are called basis for ideal, and we can write them in this way. And very particular set of for our ideal, for example, it could be the set of polynomial equations. So we can choose f1 equal f2 to be equal fk to be equal 0. So in this case, this would be really the system of linear equation. And indeed, in this case, we will see that all conditions for the ideal are satisfied, no problem. Here, however, we have some problems. First of all, obviously that the basis for the given ideal, the basis is not unique. The basis of the change of basis can be made. Moreover, so we can switch from functions f to some set of functions f to some set of functions j. And even the dimensions of this ring of this set will be not the same in general, k not equal k prime. And but okay, we can do this. Then for given ideal I, whatever, we introduced some basis. And then for given ideal I, we can define the quotient ring. So written this way, and we can then identify any two function f and j if and only if the difference between function f and j belongs to the ideal. So what it allows us to do, it allows us technically take any function and add to this function some combinations with any coefficients a belonging to the polynomial ring, such that this fi belongs to the ideal, to the basis of ideal. Well, it's obviously follows from this definition. And then at the others, or vice versa, if we have given polynomial f, we can perform polynomial reduction with respect to this basis f. So we can make these expansions and of polynomial, and there would be some remainder, something that is not expanded via this basis f, some reminder. And indeed, what we say, what I pointed out before, we want to be this remainder 0. It would be indeed the for us it would be conditions that Q system is solved. Oh, sorry, not solved. It would be indeed conditions that Q polynomials are indeed polynomials, not just Q functions. This is why it was called zero minor conditions. So, okay, it would be 2 slides later. It's clear how we connect these two parts at the very end: algebraic geometry and integrability. But before I need one more definitions, and I already switched to the slides. I need Grobner basis. Why I need the Grobner basis? Because as I mentioned already in the previous slides, indeed I have raised unpleasant situation when the basis is not unique. Even the dimensional of basis in the ring could be completely different. And I want to introduce some unique basis, well-defined basis. With each it would be it would be convenient to work. For this, I need to introduce some basis. It would be called Grobner basis, and I need to introduce some certain monomial ordering. What this ordering do? Very two simple definitions. If you have two monomials, not polynomials, just monomials, u and v, we say that u is sublinear with respect to v, and then uw should be sublinear with respect to w for any monomial w. This is just, this ordering could be any, but this property should be satisfied. And one more property that should be satisfied, that any constant should be sublinear with respect to any monomial. With these two properties, there are still big choice of freedom. What can be, what this monomial ordering is. Because we can define different powers of monomial to be leading, sublinear. We can, moreover, we have functions of many variables. It doesn't important too much. Mostly details of computation doesn't depend. Okay, details depend, but general idea doesn't depend on what particular these orders will be. We just define some order, and we choose for those who are interested. We choose the degree reversed lexicographic order, one of typical choice for this computation. And after we define this monomial ordering, then any function f belonging to ideal, there is, in any function f belonging to, not to ideal, to polynomial ring, there is some leading term. Of course, if we have order, then we have leading, sublinear, and so on. And we denote this leading term of function f as LTF. This is just notation. And this is the highest monomial in f. And what is Grobner basis? Grobner basis of the ideal E with respect to given monomial order is generating set of this ideal such that for any function belonging to ideals, there exists function J such that for any function f belonging to the ideal, it could be its leading term is divisible by leading term of this Grobner basis. And I'm afraid actually that here it should be even more. Here f should belong to the whole polynomial ring. So Grobner basis is defined in this way, that on the level of leading monomials, every leading in every elements belonging to this polynomial ring, in every function, leading monomial should be divisible by leading monomial of any coefficients in Grobner basis. Hopefully this notation is clear. I don't know whether there is question to this definition. This is one of definition of Grobner basis. There are other that could be proven to be equivalent. Okay, if there are questions, maybe time to ask. If not, we can proceed. Okay, basically, what I say is that there is certain way to define some convenient basis in the polynomial rings, in the ideals of polynomial rings. Okay, if no questions so far, we want to define a little bit more. In addition to, so we define this Grobner basis. However, in general, Grobner basis itself is not unique, and minimal Grobner basis should be could be defined just by polynomial reductions of all elements in Grobner basis by all other elements in Grobner basis. We just perform this reduction till the moment when further reduction could not be performed. And in this way, minimal Grobner basis is defined. And then one more operation could be performed such that in reduced, we can establish reduced Grobner basis. This is just a very convenient basis when all leading terms are equal 1. In this case, we finally arrive to the basis that is unique, this certain theorem from the theory of polynomial ring. And okay, we define the single convenient minimal Grobner basis, some convenient basis on the ideal of the polynomial ring. And now, using this Grobner basis, polynomial reduction can be performed and quotient ring could be defined. So what I want to say, it was introduced 2 slides ago, that any function belonging to our polynomial ring could be expanded into this Grobner basis. Now it's just some single well-defined unique basis, and there would be additionally some set of reminders. This is how we define quotient ring. And then in canonical basis, quotient ring is chosen in such a way that it's all monomials that are not divisible by any element among leading terms of anything in the Grobner basis. Well, not very clear how it's... I'm not very sure that it sounds clear, but the definition is very normal. Everything that can be defined by this linear, the leading term in the Grobner basis is already in the ideal. Everything is not, it's reminder. So we just defined it, something is not divisible by these guys. And this is indeed quotient ring with good defined basis. And then there is a very important theorem that the number of, okay, so F1, Fk, as we say, it's basis into our ideal. And if we define F in this way, then there is a theorem that the number of solutions of this equation is equal to dimensional of this quotient ring. So the number of solutions of this F that define basis into our ideal is equal to dimensional of a reminder. Okay, if no questions so far, we want to define one more mathematical object, and after this we will be finally able to formulate a connection between where we started from. We started from some integrability, and we want to end up into some we won't end up applying our theory of algebraic polynomial rings to solving our integrable problem. So what we are missing for now, we defined this basis of reminders via quotient ring, and we need to introduce indeed this basis into this reminder. Fortunately, we know even dimensional of this basis because it corresponds to dimensional of our space of solution of equation into ideal. And then we can, for any function belonging to our polynomial ring, polynomial reduction could be defined or performed. We already defined it, and it denoted by this tilde. And now we would perform reduction with respect to not just random basis in the ideal, but with respect to the most convenient basis, that is Grobner basis. And in such a way, for any function can be in our reminder can be expressed via this canonical basis in the remainder, and we obtain, coefficients on the expansions, this MF, we know their dimension, it's NS, so the dimension of set of, the dimensional basis of remainder, and this is MF is called companion matrix of F. So, at this moment, let's formulate once more. We have polynomial ring. There is some ideal in this polynomial ring. The most convenient basis, the minimal, the uniquely defined basis is Grobner basis. In this ideal, we perform expansion of any or reduction of any element belonging to our polynomial ring with respect to this Grobner basis, and what we obtain as a remainder itself we expand via basis, via some canonical basis into a remainder. This is the only state, and we always keep in mind that our choice, particular choice of our basis into our ideal, not even basis itself, of our ideal is the set of polynomial equation f1 equal f2 equal fk equals 0. And we then denote the solution of this equation by this letter, and then there is the following theorem. If we have some function f, polynomial function, or actually no, here I probably even rational function f, and we perform this summation of this function with respect to all space of solution of this equation, then the answer for this sum is given just by trace of companion matrix. And this is basically key formula for us. It would be clear next slide, or okay, it would be clear one slide later. Just few very important properties for companion matrices. First of all, they could be companion of the sum of matrix is the sum of companion. Companion of the products is product of companions, and moreover it could be expanded in both ways, and the ratio of companions is companion of ratios. And moreover, from this we automatically get the following setup, that the following properties, that we can deal not only with polynomial function for which everything was introduced, but with rational functions, because there is this property. And of course, as long as the denominator doesn't have zeros on the set of solutions. Hopefully, this is key property that we need, because so let us now clarify main algorithm, what we started from. Back to integrability. As you remember, we had 4-factor series in some moment. And in this moment, let us remember that we deal with a spin chain. Let us clarify for let us stop for a second and say that spin chain was rational spin chain, so x66 model. In this case, we explicitly see that Bethe equation and correspondingly TQ equation or QQ equations are just polynomial functions. Slavnov determinants that we mentioned that were part of 4-factor series are rational functions. Godin determinants that or normalization of eigenvectors, rational function. Transfer matrices that were in 4-factor sum or their eigenvalues are rational function. Indeed, we have our 4-factor series is just sum of some rational function with respect to some set of solutions, or with respect to all possible solutions of Bethe equations or equivalently QQ equations. So we're dealing exactly as the situation of the previous slide. We sum up some rational functions with respect to solution of polynomial equations. So then, as a result from previous theorem, we know of all that I explained previously, we know our algorithm of action. So we have the set of QQ equations, that now QQ equations would be our ideal, and we build just Grobner basis of these equations. And indeed, zero remainder conditions, it's indeed requirements that our ideal is ideal, that everything would be expanded in the Grobner basis, there is no remainder. Then, using Grobner basis, we defined for all set of polynomials in our ideal, in our polynomial ring, we define canonical base, we define quotient ring, and then build the canonical basis. Fortunately, we know dimension of this canonical basis. And then, using both Grobner basis and quotient ring basis, we build this companion matrix that I mentioned on the previous slide. So, instead of this giant sum over all possible solutions of QQ equation, that if, for example, if we want to solve QQ equation recursively somehow, numerically, I don't know, that would be a huge set of solutions. And then we should substitute this set of solutions here. Instead, we just build for our Q basis the Grobner basis, then expand this all factor or make quotient ring with the Grobner basis, expand everything in build then companion matrix, and then we know that the answer for this full sum is just trace of companion matrix. And this is key formula for our work. Any question at this moment? Because this is like key formulas. This two, I would say. This one.
Do you have some multiplicities of your solutions? Do you have some problem with this?
No, with QQ functions explicitly, if you are talking about overcounting of beta roots, QQ functions are defined explicitly in this way that there is no overcounting.
So it's guaranteed that you don't have some solution with some multiplicity.
No. The only is still missing is the rational case infinite beta roots are missing. So they should be added by hand. You got what I'm talking, hopefully.
Can I ask about the formula on the slide? I don't understand. Summation over xn, and then there are x1 up to xn appearing.
Yes, this x is the set. It's a set of x1, xn, such that satisfy this set of equation.
So x1 up to xn are solutions to your QQ system.
Yes.
And then summation is over all of them.
Over all possible solutions, yes.
Just xn. It looks like there is just the last one, so it's confusing.
No. It's supposed to be bold. Unfortunately, I'm not sure that it's clear that it's bold font. It's bold font in sense that this is full set.
Okay, thank you.
Use head, please, next time.
Sorry? Okay. Should we proceed further? Hopefully we can proceed further. So, okay, now at this moment, I basically defined the way how to compute everything. The only thing that I didn't mention, I would not mention because I don't know, it's how to compute Grobner basis. And this is a major problem because there is technically no way to compute a Grobner basis in some unique, convenient way in general situation. The idea is following. Technically, for factor sum that I wrote to you, this formula is sort of very general. In general, if I deal with rational function and I want to sum up this rational function with respect to all solutions to some equation, this formula is go on. It's good. And technically it's true for integrable system, not integrable system, not one-dimensional system, not one-dimensional. It's true even to something that's completely unrelated to physics. The only problem, how to find Grobner basis and how to construct companion matrix. And here it's where the two of our co-authors did the main part of this job, and it's very computational heavy because this is a computational algebraic geometry, as we call it, or as it was called before us. In fact, you should use certain algorithm, so call it Buchstabe algorithm or F4/F5 algorithms, in order to build this Grobner basis And next you should perform this polynomial reduction. Next you should build companion matrix. And this is complicated. It's just a procedure without any good defined general way. Well, there is certain algorithms, but in general you just use mathematical packages. Fortunately, proper software exists. But okay, the good point is that you dealing here with exact solution. So take into account, you don't perform any approximation. You don't solve your QQ system approximately. You don't have anything of this. Technically, what indeed you build exact companion matrix and you consider exact trace, but with the price of huge computational power and huge computational time. So after this remark, I think I can present some of results that we computed. We don't have too much time and results raise bulky for general case, but okay. Let's back to our correlation functions of our quantum circuit. So once more, remind you definitions. Omega is just this vacuum. Sigma hat are just the string operators. And then in general, they have some special separation. And most important, that have time separation because of this evolution operator. Evolution in time in vertical direction, if you remember. And here, n is the length of these strings. And k is just time and special separation correspondingly. K equals 0 is basically discrete version of what people usually call it logarithmic echo. So logarithmic echo is just evolution from one state to the same state. Probability of return of quantum system to the same state. If k not equal 0, it's not too big complication here because there would be just additional factor. In this particular initial state, it's just very simple setup. And now we give the basically what we have in general. We perform solution indeed of the whole QQ system with this transfer matrix of time evolution. And there are these coefficients that are given by ratio of Slavnov's determinant, Godin determinant. And first few answer for just so here is just a time evolution. Here is the length of the system. We consider just system of length 2 with one magnon. Okay, some very simple solutions. B and C are functions from our 6 vertex R matrix from Archer. Okay, there are what they are. They are very simple, of course, for the system of length 2 and just from one magnon. In more general case, when as you see for already like for case of length 3, 2 magnons, for case of length system length for 1 magnons, keep into account that actually system is twice bigger than here because we have system length 2a, not a. Well, the answer quickly become more and more complicated, and of course I don't even in paper we don't give general setup when system size is 20 qubits. Because in this case, it would be too complicated to write it down. We just enclose to our paper some mathematical file where you can find all result. So what is good about this result? Let's say in this way. Indeed, it's complicated. It's sort of even to write down. However, this general result, in sense, for given initial state, this is just result. First, it's exact. There is no simplification, no numerical solution, nothing. And then this is just results that could be computed for any system length, reasonable, for any amount of magnons. It could be computed for any anisotropy. Technically, all anisotropy of Hamiltonian is given by this eta parameter. And for any time, for any period of time. The time, as I remember you, it's just evolution number of steps of how many times we applied operator of discrete time evolution. And okay, what we can compare here and what conclusions could be made about what interesting observation can be made here. So first of all, in addition to this initial state that I consider this simple string that we denote sigma hat, there is also sigma tilde. And sigma tilde is so-called nil state. So the state where at neighboring side there is additional sign minus, and then it's basically tensor product on neighboring sides 1, 2, for example, it's 1, 0 minus state 0, 1. This very also convenient and very often set up in both theoretical study and experimental study for initial state. And what we can do, okay, technically after performing four-factor summation, as I say, resulting expressions are very, very bulky, even for relatively small system. For the system size of 20 qubits with 10 magnets, it's incomprehensibly huge. However, we can, one of important observation we can make, maybe interesting observation about distribution of poles of these systems. And this is very important, very remarkable, that in fact, if you would consider this one-dimensional system with a time evolution, you can consider just as two-dimensional static system, then these poles would be so-called Lie-Yang zeros. In our work, if we treated this two-dimensional system, totalized system, as evolution of one-dimensional with discrete evolution, then it would be some Lie-Yang analogs of dynamics, analog of Lie-Yang zeros. And then we see that actually for these two setups, distribution of roots in dynamics is very different. For this type of setup, for just initial string, all condensation of zeros are in lower half plane, zeros of our Loschmidt echo, or our correlation function, if you wish. And for nil state, condensation happens in both upper and lower plane. And usually, presence of these condensation curves means that there are some phase transitions, so multiple phases. Of course, phases we are talking if you consider it's like a two-dimensional static system. If it's one-dimensional system with dynamics, and it's a little bit different situation, but indeed I don't have time to go into details about this. Also, there is an interesting connection with Baraha-Kahane-Weiss theorem that it says that for function of this type, and this is exactly type of we have time propagation, eigenvalues of transfer matrix is time propagation with power n, so it's just a number of steps how much time we apply this propagation operator in the right direction. And basically here is just some coefficients that don't depend on this propagation. Then we know that in n equal to infinity limit, the zeros are either isolated, either condensated along curves, and the condensation of zeros along curves indeed means that there are some degeneration of these eigenvalues. So if there are few different curves, few coinciding eigenvalues or corresponds to appearance here of these condensation curves. Okay, I think I should probably proceed to the finish. Yeah. So let us a bit summarize this work, and let it once more stress that up to the moment when four-factor expansion is done, it's indeed easy job, and it was done already 4 years before. However, starting from that moment, explicit computation of four-factor sum and exact computation, not some numerical computation, was complicated problem, and our main goal was solve this complicated, a little bit applied problem. Despite pretty strange apparatus of this polynomial ring theory, the problem itself is very applied. And then you would ask, but we consider the same system of 20 qubit sites. Why so small system? Well, because it's this is the point of the work. System size of approximately up to 20 qubit, it's what is used in experiment. And actually, it's raise the simplification, because if there would be more than 20, if there would be not 20 but 200 qubits, you would very confidently proceed to thermodynamic limit in the system, and you know how to deal with thermodynamic limit in Bethe Ansatz and so on. If it would be not 20 qubit by 10 qubits, okay, then you just make numerical solution and don't worry. 20 qubits, it's very unpleasant situation, because indeed it's a bit too big to solve numerically. Of course, you can do it's still matrix by just transfer matrix of size 1 million. You can solve it numerically, but with some problem with precision, with some problem with long time evolution. So as a way, so this case of medium size is exactly the situation when small, it's too big to solve by brute force diagonalization, too small to proceed thermodynamic limit. And we believe that in this case, actually, this computational algebraic geometry is one of convenient tool. Of course, as I mentioned already, why this problem was important per se, because this running of time of this discrete time evolution of quantum circuit is a typical test bed for quantum computers. Then, okay, in one observation, and in long time limit, of course, it's correspond to some thermodynamic limit of partition function of the cylinder. I sort of already discussed it, that we can consider this like one-dimensional evolution in time or in discrete time, or just two-dimensional partition functions. And then perspectives, well, there are a few perspectives here. So first of all, this very particular situation when our deformation parameter is at root of unity. And for a long time, it actually was some problem, because QQ system only recently was derived for this very particular case. Then some possibilities here to proceed to nested Bethe Ansatz, including something like Hubbard or TJ model, because technically, when we deal with such small system, we don't need even determinant representation for scalar products or this overlaps. It raises a problem in this situation that nested Bethe Ansatz Grobner basis would be more and more brutal, more and more computational heavy. And well, also, of course, there is always a degree of freedom to choose different configuration of this initial state. Not just domain Voronel states, but a little bit more. Basically, I'm finished.
Okay, thank you for your talk. So we are a little bit over time, but probably there are some short questions. Questions during the talk. So thank you again for the talk.